Swayam Prabha. Digital India. Educated India.
Welcome to week 7 of our NPTEL course. We are in week 7, lecture 2. So, we are going to talk about the aeroacoustic state variables that I kind of just mentioned at the end of my last lecture. So, aeroacoustic state variables, that is what we are going to do now. So, these obviously come, these basically the need for obtaining or defining new variables, aeroacoustic state variables, means that we want to add a few extra terms to the classical variables. So, in order to better suit, incorporate the convective effects of mean flow, Mach number m naught. So, the total acoustic energy flux or acoustic power that is carried by a mean flow is given by m dash and a dash, where the bar indicates really an average over the radius. So, m dash is your perturbation in the mass velocity. So, this is your rho naught plus rho tilde and s times u naught plus u tilde and minus rho naught s times u naught. Okay. So, now when you multiply out the terms, that is rho naught u naught s and rho naught s u tilde, and then we do rho tilde s u and rho tilde s u tilde minus rho naught s u. So, let us see what happens. This thing goes away and these terms again will drop out, because rho naught and u naught, they are multiplied, they are second order quantities and they will be much sort of smaller than your other quantities, that is your u tilde and this one and this one. So, basically after a little bit of algebra, what we get is the perturbation mass velocity is nothing but rho naught s u tilde plus rho tilde s u naught. So, this is what we are going to get, and this we can write as perturbation mass velocity plus your p tilde by c naught square times s u naught. So, we can further sort of simplify these guys and write p tilde into s by c naught into u naught by c, which is your v tilde, and this is nothing but your y naught, and u naught c naught is nothing but Mach number. So, we have an expression for the perturbation mass velocity when you have a non-zero flow, which is your this thing. Clearly, when m naught is 0, you again get back m dash is v dash, that is nothing but acoustic mass velocity, that is the perturbation velocity. The same thing we are getting here, but an extension of what is done in the classical variable. The classical variable is just v dash. Please understand this point clearly. The classical variable is just v dash, but when you have a mean flow of Mach number m naught, then you need to add an additional term, which is your this thing. Now, similarly, we can also try to do in this short space what happens to the stagnation perturbation stagnation enthalpy, that is your p naught plus p tilde by rho plus your head, that is, we saw that only briefly in the last class. So, this thing minus your p naught by rho naught plus u naught square by 2. So, now we need to do some algebra, but I will sort of skip that because we have already done in the last class. Entire idea is about cancelling terms. It is clear that these terms and this term will cancel away and this term will be retained and some second order terms will drop out. So, once we do basic things, some simple algebra, we are going to get p tilde by rho naught plus u naught times u tilde, exactly what we saw in the last class. So, I need to go to the another page and kind of simplify what we just saw here. So, u naught can be written as m naught into c naught, is not it? So, that is what we are going to do, and actually we are going to say something like this, is p tilde by rho naught, and u naught c naught we will multiply and divide the numerator and the denominator, and we are also going to do the same thing with the cross section area S. And remember what we get here, there is no rho. So, if we multiply here by rho naught, and there is u naught times this thing. So, here we had also u naught, actually I am sorry, and this was something like this. So, if we divide by density also and then happen to take the density common, ambient density mind you. So, this particular term will be m naught, is not it, and c naught by s will be 1 by y. So, and this entire thing will be mass velocity. So, we will get your m naught y naught into v tilde. So, this is your this. So, we have your first equation and second equation, we have these kind of things. So, basically what we see again, that when m naught is 0, we again get back pretty much the classical variable, but it is just normalized by the ambient density. For air it is 1.20 at standard temperature and pressure. So, now we need to worry about what are we going to do with these variables. So, one thing that obviously comes to our mind is use equations 1 and 2 basically back in this particular main thing from where it all sort of started. So, clearly here, as stagnation enthalpy is equal to the stagnation pressure divided by the ambient density, J dash is the perturbation stagnation pressure divided by the ambient density. So, now what we are going to call then, that this entire thing, let me call this as PC, okay. And similarly this entire term is basically denoted as Vc. So, the reason that I sort of brought this out suddenly was that it will be very convenient to write out the power in terms of the convective state variables. So, C here, subscript C, basically it means convective state variables. So, here we have this, okay. We have got this kind of a thing, all right. So, Wc is equal to 1 by rho naught into Vc Pc, and you have an average over that, okay. So, now clearly we have defined these quantities and expressed the total power that is radiated in terms of the convective state variable. So, how about we write in one dimensional Muffler analysis, as we have been noting from the beginning of this course, that transfer matrices are probably one of the most easiest way to analyze a more complicated system. So, basically we must sort of develop a transfer matrix relation between the convective state variables Pc using some transfer matrix between P and V, okay. So, how do we do that? This is m, this is m naught by y naught and m naught by y naught, and this is 1, okay. So, this clearly follows from this one, this equation 2 and equation 1. So, we are doing nothing but we are just calling this as Vc. So, Vc is this thing and your Pc is this thing. So, we are just expressing Pc and Vc in terms of, that is convective state variables, in terms of your classical state variables. Now, clearly when m is 0, m naught is 0, we get back what? The identity matrix, and that basically your convective variable is equal to the classical state variable. So, now we need to probably go further. So, how do we go further? We will basically put P as usual, the usual business, A plus B, forward wave, backward wave, and setting the coordinate system 0 at that point, and V is nothing but A minus B by y naught. So, when we do all those things and use these relations in the box here, so we will get P tilde plus m naught y naught V, we will get after some algebra and B times 1 minus m naught. So, now here is an opportunity to define yet another variable, calling this as AC and this guy as BC. Okay. So, we have got this. Now, PC P tilde C is nothing but AC plus BC. In a similar manner, where AC is, let me write it down again, it is nothing but progressive wave variable, but it is now strengthened by the mean flow, and this is nothing but B, but this is strengthened by this thing. You know, for a mean flow along the positive x direction, significance of this is that the waves that travel in the forward direction, they are strengthened by the mean flow m naught, and in the opposite direction it is natural that they will be weakened. Okay, they will be weakened. Now, similarly, what about Vc? Vc is nothing but V tilde and m naught times P by y naught, and this is, after some algebra we will get this sort of a thing. So, this is AC minus BC minus y naught, okay, where you have pretty much the same relation between AC BC with A and B. So, they are the same, that is defined here. Okay. So, basically the entire idea is that just like decompose the classical state variable pressure P into A plus B and classical mass velocity in terms of A minus B, the same thing we can directly decompose the convective state variables in terms of AC and AC BC, and similarly Vc volume velocity convective term can be decomposed as AC minus BC divided by y naught. The idea is that to incorporate the convective effects of mean flow. Now, clearly we would like sort of again go back to this particular expression and see and kind of relate or write down the acoustic total energy flux that is coming out of the duct in terms of this thing. So, we saw in the last class that Wc was this we just saw now, but what I am saying is that we saw that this was nothing but this thing this thing. So, here we have 2 rho naught y naught and AC square minus BC square like this. So, we have this kind of a thing. Okay. What do we do for this thing? We have your Wc given in terms of the convective state variables. So, we as usual reflection coefficients were defined in the week 3 or 4 as B by A, and now the convective reflective coefficients, it is natural to see that they are defined as BC by AC, is not it. So, what it would mean is that the total acoustic power that is carried by the waves in the duct with a mean flow, this guy can be written now as Wc as nothing but your AC magnitude whole square divided by 2 rho naught y naught into 1 minus mod of Rc square, is not it, and your Rc will become nothing but BC by AC. Okay. So, this is nothing but B to 1 minus m naught and A to 1 plus m naught, and this is what we are going to do. Rc. We have this sort of a thing. So, reflective coefficient Rc is R times 1 minus m naught divided by 1 plus m naught. So, now what it means is that in case of convective waves, the reflection coefficient Rc necessarily magnitude, this is a complex quantity because remember R is also complex, but the good thing is that the magnitude of Rc should be less than 1. Why? Because now when m is non-zero, so let us say it is a we can ascribe any number, we can sort of verify this. We can put one m naught typical values of 0.15 or 0.2 maximum value that sort of we can get. So, we get basically your 0.8 divided by 1.2 or something like that. The point is that RC will always be less than 1 because m naught is positive. Your denominator will always be greater than 1 and numerator will be less than 1. So, this is just one sort of example. Since this guy has this relation RC reflective coefficient is always magnitude of that is less than 1, what we could further come to the conclusion is that 1 minus m magnitude of R of this is less than 1 and R should be 1 plus m 1 minus m. Okay. So, we have this sort of a thing, reflection coefficient magnitude of that is less than equal to 1 plus m divided by 1 minus m, all right. So, basically m, like I said, it is positive. So, in presence of your non-zero mean flow or non-zero Mach number, although small it is, reflection coefficient can be greater than 1. It should be greater than 1 because your denominator is less than 1 and this is this thing. So, that is one thing that obviously comes out of all these calculations, and clearly the total aeroacoustic power that is given through a tailpipe. So, if we have something like, by the virtue of all the expressions that we derived so far, the reflection coefficient for the classical wave variables can be greater than 1 when you have a non-zero mean flow in a duct, but in typical case it is less than 1 or equal to 1. Now, going back to the previous slide, we have RC which is always less than equal to 1. So, after doing all this thing, what does it really mean? It really means that for a moving medium, when you have a reflection coefficient measured with a static probes, that can exceed unity. That means when you are measuring the reflection coefficient with a static probes, the reflection coefficient in presence of a mean flow can exceed unity. However, aeroacoustic pressure can be picked up only through a total or a stagnation probe facing the flow. So, another thing that I want to point out here is that the forward waves, as we can see, this is pretty obvious from the from the underlined terms. The forward wave is really A, amplitude of the forward progressive wave is A. So, it basically gets strengthened by 1 plus m. So, you have A into 1 plus m, all right. So, what it really means is that the forward wave gets strengthened with the mean flow by a factor 1 plus m, all right. So, and the power or the acoustic power associated with it also gets strengthened by 1 plus m square. So, basically the incident power in the presence of flow basically gets it's increased by a factor of 1 plus m square. So, we can work out typically for a automotive muffler, as we have discussed, maybe 0.15 or 0.2 maximum can be the flow velocity Mach number. So, how much would be the power associated with it? We can do some calculation. If you have 1 plus 0.15 square, so it is 1.15 square, and how much it is, and let me figure out in a minute. So, that is about 1.32, basically a 32% increase for a typical maximum flow velocity for automotive mufflers. So, that is quite a lot, 32% increase. Another thing obviously that is also obvious from these expression is that the wave that is going back is diminished by that much amount. So, you have B into 1 minus m. So, the reflected wave is diminished by that much amount, and the power is also diminished by a factor of 1 minus m square. So, that basically that would mean it is about 0.85 square, which is about 0.7273 you can say. So, it is about 27% reduction in the acoustic power that is carried by the backward propagating wave. So, after having discussed all these things, one thing that really comes to our mind, look, really we have a system something like this. You have a tailpipe, and remember when we first started talking about acoustic real world application, we had a situation like this in which waves are being incident, and this is a really an open end, there is no flange, and that is something what we did I guess in week 3 I believe. So, that was far more complicated. We have those expressions for the radiation impedance, and that was basically given by your Z naught is equal to R naught plus J X naught, where R naught and X naught are the reactance or resistance and the reactance respectively, and only for low frequencies this is about K naught square and 0.5 K naught R naught square plus J times 0.85 K naught R naught. Okay. So, this is what it was. So, this was the classical wave when due to the this is the radiation impedance imposed by the atmosphere. So, you have some waves that are basically reflected back from the atmosphere. So, now a similar question that should come in our mind is that what happens when we have not just a stationary medium, but you have a flow, mean flow along the direction or along the axis or the duct. So, when we have such a thing, we would like to find out what happens to the total acoustic power radiated and what is the reflection coefficient in terms of this thing. So, these are sort of very much related to your resistance part of the atmospheric impedance. So, let us see how we do that, and before we begin discussing this, let us first also understand that let us write down the expression for the total acoustic power that is radiated by the flow. So, we have basically a potential core. When the flow comes, it collapses, and this is your potential core, and then there is a shear layer. There is a shear layer in which the rapid mixing of the jet happens. So, although it is like a by the time it comes, it is not a supersonic jet, it is pretty much a subsonic jet, but you still would have a potential core, and you have a top hat profile, and gradually becomes a Gaussian profile in the downstream. So, you would have this is the mixing region really, and or the shear layer as we say, and shear layer. And so, if we want to measure at a certain point what happens to the at a certain radius radiated, we could do that. And so, we begin again with a typical thing. You have your A and AC and B and BC, your backward travelling reflected convective part. So, the total power that is radiated WT is equal to 1 by 2 rho naught into Y naught into A into 1 plus m whole square minus this is of course your square and something like this, all right. So, we can actually write it a little more cleanly, S divided by 2 rho naught C naught, something like this. We have this sort of a thing, and let us see how we how do we interpret all these things and why should it be useful. So, this WT is the total acoustic power that escapes from the pipe in the presence of flow, and actually there is much more to it than what just meets our eye in this expression. This basically all this A B or A into 1 plus m, B into 1 minus m, all these things basically tell you the sum total. We are really interested in the net quantity, and this is really the sum total of the total acoustic power contribution by monopolar dipole sources that they directly contribute to the far field, and also because of the vortex shedding that happens in the wake. So, it is sum total of all the direct field sources and the sources generated by vortex shedding in the wake that contributes to the far field noise that is observed at the point F. And another thing, basically what people figured out from their analytical derivation is that WF is, which is basically the overall effect of the radiated power, is a new expression. So, it is basically is the measure of the total power that is radiated from the jet. So, that is your spherical surface area into the intensity, that is your IF. When you do that, this is approximately equal to WT, that is the theoretical power that is we obtained from this expression. When you have an outgoing wave, that is wave that goes in this direction, the interaction of the outgoing waves with the shear layer or with the jet itself, it produces some sort of a back reaction on the wave. So, as a result, it is not that the entire this power is radiated, a fraction of that power is radiated, and that is given by Wt. Empirically, people have found out that this is given by Wt into k naught r square divided by 2 m naught plus k naught r whole square. Okay. And where IF is the intensity over a spherical surface, 4 pi r square is the hypothetical sphere with the radius r and centered at say a point on the duct, or probably it can be some point just at this point. Okay. So, we have this sort of a thing. Now, Wf is this. So, what it means is that the log of the difference, if we basically were to take log of Wf by Wt and take 10 times log of this, it would be abundantly clear that we have this sort of a thing. This is the logarithmic difference of the total power theoretical or the actual power that is radiated by the jet to the theoretical possible power. So, people have plotted this thing, and what they observed is that basically for 0, obviously one thing that is clear, when m naught is 0, this quantity is this, basically we have this quantity goes to 0, log of 1. So, basically then it is, if there is no flow, then Wt and Wf are the same, but for non-zero Mach number at very low k naught r, suppose let us put k naught r to be 0 or tending to 0. So, we would get this as 10 times log of 10 and 1 by 2 by m naught. So, basically at very low frequencies, let us say this is k naught r naught and this is your 10 times log of 10 entire quantity. It will go like this. So, the greater the Mach number, the greater the difference will be in low frequencies, and then they will converge. So, this is the result for m naught 0, this say let us say this 0.3, 0.15 and so on. So, what basically it would mean is that the interaction of the sound wave and jet, which attenuates the wave as it comes out, amplifies the broadband noise. However, this is sort of inconsequential, because even after amplification the jet noise remains insignificantly low compared to the sound wave. So, now however, what really matters is the how the radiation real part of the radiation impedance in the presence of flow, that is the resistive part, how does that vary with your flow, and people have developed some expressions like Meschel. Meschel has developed an expression in one of the references where he relates the radiation resistance in presence of flow, which is a function of Mach number m naught to the characteristic impedance of the duct as given by the following relation 1 minus 1.1 m, and this would basically mean k naught r naught whole square by 4 minus 1.1 m naught. Similarly, Panikkar and Munjal a long time back, they derived another expression, another empirical expression, which is given by the following relation. You have this thing. So, what this would mean is that like this, there you can find a number of such relation for the radiation resistance in terms of mean flow parameter. What it would really mean is that at sufficiently low frequencies, this quantity or this quantity can be negative also. So, all these things will impact the radiated noise or the radiation or the atmospheric impedance in presence of mean flow, but I guess we probably have to move now more to the development or the transfer matrices in the presence of mean flow. So, our next topic right in this lecture, before we complete this lecture, there are a couple of more things to be covered, is basically development of at least the simple expression for the transfer matrix of a tube, transfer matrix for a uniform area pipe in presence of flow. In the presence of flow. So, how would that happen? So, as we saw, the pressure, the P tilde as a function of Z, time harmonicity is sort of is implied. So, what we would do is basically P Z is given by A from our previous theoretical developments that we did when probably in the second week's lecture, the first couple of lectures. The solution was something like this, isn't it? K naught, assuming only planar waves, no higher dimensional waves, K naught Z plus this. So, I would sort of put a thing here and plus E j k minus this, okay. And mass velocity was given by 1 by K naught A okay. So, this was the case where what about K naught plus and K naught minus, and here we are typically could also consider more complicated or more sort of realistic situations such as damping or the absorption. Basically, you have in a viscous medium and a turbulent incompressible mean flow, due to friction factors and due to absorption, the wave attenuates also. So, if we were to discard all those things and consider a simple case of non-zero absorption in the medium, or basically no dissipation in the medium, lossless medium as we are always considering, because a lossy medium a little more complicated to deal with, we will keep the matter simple, and that is why above expressions will apply. There is no changes in y naught. Y naught is nothing but sound speed divided by cross section area of the duct, C naught by S, and K naught plus is nothing but wave number K naught and 1 plus m. K naught minus is K naught into 1 minus m naught. So, basically what do we do with this expression? So, what we do, let's consider K naught first. So, this is like I said written as K naught 1 plus m. So, we can sort of write this as K naught into 1 minus m naught and 1 minus m naught square. So, this I can introduce a new quantity K c and 1 minus m naught. Similarly, K naught minus can be written as 1 plus m naught. So, all these things will apply, and then under such a situation these two equations that we have, this one and this one, can be written perhaps in a little bit more cleaner form. P z is nothing but e to the power j m k c z and a e to the power minus j k c z, and this is your plus e j k c z, and mass velocity will become your e to the power j m k c z divided by y naught, and you have these terms will still go, but there will be a minus sign here sitting somewhere here, and e, all these things will happen. Okay. So, what happens is that now these expressions, let us say this one and these two ones, they are almost nearly identical with the case when there is no mean flow in a duct that is with a stationary medium, because you see the forms a into e to the power minus j k naught z and b into e to the power j k naught z. So, K c is playing the role of K naught, where as we see K c is nothing but this term that is encircled somewhere here, isn't it, K naught divided by 1 minus m naught square. So, clearly when you have m naught is 0, these expressions reduce to the old form. So, we need to recall our last several lectures before what we did. Using all this thing, it still involves a little bit of maths, but there is a reason why we put these two expressions in the form that we are seeing, that is basically to get transfer matrices derived. So, apart from this particular term, apart from this term and this term, everything else is pretty much the same. So, one would naturally guess, I would really encourage you guys to do the algebra. I am leaving the algebra for you guys to work out. How will you basically eliminate A and B? Let us say you have a duct with a flow in this direction, and between point 1 and 2 you would want to derive the transfer matrices, isn't it? So, how would you go about doing that? So, what we probably could do is that apart from this term, like I said, we have pretty much the same thing. So, we could basically just write down between the points 1 and 2, you can say z is equal to 0, z is equal to L, P tilde and V tilde. You have this z is equal to 0, and this form would be the same. Cos k c l and j by y naught into sin k c l and j y naught into sin k c l, and here you have your cos k naught cos k c l, isn't it? So, the form this transfer matrix is the same, k naught is replaced by k c, and you have an extra term which is your exponential that you just saw somewhere here. So, again I am insisting that please work out the derivation. I am just not showing with the steps involved. So, here you have L. So, let me sort of write it a bit more cleanly. So, this is e to the power minus j m into k c l. So, when m is 0, you get back your old transfer matrix. So, this is the stuff that we are really aiming for to do in this class. I mean, one of the major objectives in this class. So, now basically what we see is that we see a relation between the point 1 and 2 in terms of the mean flow. So, the corresponding what we could also possibly do, if you recall the last lecture in this week, we had this relation, this particular guy. So, what does it do? It basically does relate the convective variables with the classical state variables. So, P and V are just the inverse of this into this, isn't it? So, what we could just probably do one thing, we could now that we have derived this guy, what we could do, that this is equal to the matrix that I had shown you, that is the inverse of that, and this matrix is we could basically relate it, isn't it? So, I will just write it down, that matrix, the matrix from sort of again what was given in slide 16. So, the inverse of this matrix times this particular guy is this thing. So, basically what will happen is that I can, instead of P and V at z is equal to 0, I can write this entire matrix inverse times P c V c at z is equal to 0. Okay, this should be sort of quite clear to you guys, that P c and V c tilde of course at z is equal to 0. So, we have this guy sitting here, this thing. So, we have this, but actually before we do that, we probably should be writing 1 and m naught y naught m naught by y naught 1 inverse P c V c at z is equal to 0. This is equal to your e to the power minus j something and the matrix that we just derived now. Now, we have this thing. So, we what do? Instead of this thing, so let us go back to slide 16. So, this again we have to invert this. So, inverse of this times P c V c at z is equal to L is what is going to do the trick for us. So, here we have no choice but to invert it and write P c tilde V c tilde at z is equal to L. So, this is 1 m naught y naught m naught y naught and 1. When we now we need to pre-multiply this thing. So, basically what it would mean is that P c V c at z is equal to 0 okay, is inverse of this. So, inverse of this you need to multiply basically with the same matrix again. So, what we would basically end up is your e to the power this quantity, this is there, and here we have 1 m naught y naught m naught y naught 1 and then this guy this. Now, the inverse of this has to be written. So, when we do some linear algebra, you could go to some symbolic package Mathematica, Maple, or do some hand calculation and figure out for yourself that the inverse of this matrix is nothing but 1 into 1 minus m naught y naught and minus m naught by y naught 1, and here you have your PC VC at z is equal to L, and of course here it is 1 minus m naught square. Okay. So, after all this algebra we get this. After basically pre-multiplying and all those sort of stuff, the equation that I just sort of presented here, that will very cleanly reduce to the following form: PC tilde at z is equal to 0 into e to the power minus j mkcl times your cos kcl j by y naught times sin kcl j y naught times sin kcl cos kcl times PC VC at z is equal to L. Okay. So, we clearly see that even the convective state variables relation, the transfer matrix between the convective state variables at z is equal to 0 and z is equal to L, they remain intact. So, it has pretty much the same form as this guy, and then this basically can be used for a number of other things, like connect variables between discontinuities, and where we have to include loss factors which are basically found out through experiments in the literature. So, we will discuss about couple of discontinuities in the next class, like extended inlet and outlet discontinuity, and how does that reduce to the sudden expansion type of discontinuity, and probably get some simple expressions, and perhaps why do we need to why we do not really consider a discontinuity as it is. I mean to say, in spite of all these things, all the things that is taught in the last few weeks and this thing, we would probably never use the muffler, just use something like this sort of a muffler, or probably would even never use an extended inlet and outlet just like this. We would do something here to connect this thing through perforated bridge, otherwise flow creates a lot of problems. You would definitely need a perforated bridge. So, all these things are subject matter of the next lectures in this week. So, why do we need perforates and little bit background and all that. So, till that time, thank you, stay tuned.